All right, welcome everyone, and it's day 2 of our session. That's the joint MeteoData and then PY4CA sort of webinar series, and there's a second out of the 4-day series. And just as we did the very first day, I'm going to go through the tutorial material, and then I'm expecting that it should last about approximately 45 minutes, between 35 to 45 minutes. And then beyond that, there will be time for more oral questions. But then while I'm going on, if there's the need to interject, you can always use the chat. Just type in what questions you have, and then I'll be able to respond to you. I believe I'm loud enough. You can hear me from wherever you are. So once that is sorted, then it means we can go ahead. All right, so first and foremost, today is Ghana's independence, so happy independence to all our Ghanaian partners and our Ghanaian participants. All right, okay, so if you go back to the GitHub page, you would see that there's an update. Now we have the day 2, and that's what we'll be working with. So you could easily download the whole code as a zip form, or if you are familiar with Git, you can just use a Git to pull it. Go to the Git and then Git pull this onto your local machine, that's your local PC. Now you can equally link this to your Google Colab, so you can just open this directly from Google Colab and work with it. Alternatively, if you don't have the application, what we've done is we've just placed the launch binder logo here. Once you click on this, it should open something like that for you. It should open this with the day 1 IPython notebook, but then you still have the chance to select the day 2. So if you click on the file browser here, you have the day 2 notebook, and you can just click on that, and that loads the day 2 notebook, and then you're able to follow through exactly what I'm doing, so that if you have any questions, it's easy, and then we know where you are stuck and then how we can help you. So that's what we'll be working with today. We noticed that last time we sort of exceeded our time a bit, so today we want to have it in a bit controlled form. We'll first and foremost start with the task that were in the last session of last week, but before that we'll look at some quick visualization. So we'll start. Our outline today will be just 2 main things. We look at the visualization in Python, and then also the application of the where method. So I believe when we get there, we'll throw some more light on it. So the beauty of Python is that it's unlike some earlier basic languages, this is quite robust. It's more object oriented. It also has some good visualization. So you don't need to do your sort of computations and other things in Python and then sort of do your visualization somewhere else. No, you can do all of them in here and it works. And so what we'll look at in the first aspect is the quick looks on visualizations, be it a simple visualization or if you want to have multiple panel plots, how to go about that. And so in Python, every visualization package you would see has matplotlib as its fundamental. So whether you are using Bokeh, you are using Seaborn, you are using any of the other plotting tools you can think of, it is fundamentally written on the matplotlib. Okay, and so matplotlib is just the plotting library, and it has similarities to how plotting works in MATLAB. So that's the default interpretation of the name. And so if you remember from last week, we talked about how to import the packages. Now, Python makes the work easier in the sense that you don't need to draft everything from scratch. You have the packages. So we have the matplotlib, which is the plotting library. And so to import that, you can just type in here, import matplotlib. And this is pulling out the huge matplotlib package. But then we don't want everything from matplotlib currently. We want just a sub package. So if I should add a dot and I tab, Ideally, we would have had what's the name? All the children packages under Matplotlib. Yes. So like what you see here, all these are sub packages under the Matplotlib, which perform different roles. Others are for color controls, others are for animations, others are for the figure panel controls and all that. But currently we are not interested in all these ones. We just want the PyPlot, which is just one of them. And so if you want to get this, then it means we just add a .pyplot, and it means we are importing just the child package pyplot from Matplotlib, not the entire Matplotlib, just the pyplot. And whenever you call this, you notice that we had the parent.the_child. So if there's a sub package under this, it means we are always going to type this matplotlib.pyplot.the child package. And because we don't want to be doing this all the time, we just give this an alias. So just give it more like an alias or a nickname, where when you call that nickname or you call that alias, the alias pulls out that whole package with all the child functions. And so that's what we have in the first line. So we're importing matplotlib.pyplot as PLT. So that means whenever we call PLT, so for instance, let's say I run this, and then now I need the sub packages under PLT. If I just type PLT dot, all these are under PLT. All right, so I don't need to now call matplotlib.pyplot.say echo or matplotlib.pyplot.angle_spectrum. No, I just call the alias, and then it pulls all the sub packages under that, and then I can pick any one of them, and then I work with just that one. Okay, you can import it this way. The other option is you can equally say that from matplotlib, that means from the parent, import just the child, which is the pyplot. There's another option. So from matplotlib, import pyplot as say PLT. And this is similar to what we have down here, right? It performs the same function. All right. And we've also similarly imported NumPy, which is numerical Python, because of a sample data would want to use. Actually, we wouldn't really need this, particularly for what we'll be doing in the NetCDF data handling today. But then just to make the visualization complete and from the basic perspective, we would import the NumPy as NP. So once we import this, it means we have NP, and then all the children packages or the child packages under NP is accessible to us. So everything numerical, whether finding the absolutes, finding the whatever, all the things under them, we can access all of them. All right. Now, currently, if I want to generate, say, random numbers, I just add my np.random.say rand and generate, say, maybe 10 random numbers. All right. And these are just fractions. If I want to include negatives, then rand n, and then also I get my positives and negatives. We'll be using this in a bit. That's why I'm explaining that. All right. Okay, so now to the figure interface itself. Now think of it as you have a drawing sheet. You have probably say A4, A3, A2, whatever sheet it is. That is your entire canvas. And you decide to split it into, say, portions or panels, or draw everything on that entire canvas. That is yours. So once we imported the matplotlib.pyplot as PLT, to get the figure interface, we just have the plt.figure. So this is basically generating the canvas file. So plt.figure just generates the figure canvas for us. Okay, and so it tells us that we have a figure generated with this default size, and then it has no axis. The axis comes in when we are dealing with the individual panels. Currently, this is just one plain figure, so it's not giving any axis. So this is just a default canvas. And then once we've created this, we can plot anything. Let's say I'm plotting, so plt.plot, and then I plot, say, the list 1, 2, 3, 4, 5. Okay, exactly. So that's what we have. Let me intentionally change some. So let's say we have 10 here, we have 39, so that it wouldn't be a linear plot. Say 4.2. Okay. Yeah, so with this now you can see clearly the variation. So first we had 10, and then from there there's 2, and then there's 39, there's 4.2, and then there's 5. Now what we're doing here by default is when we are plotting, because we created the environment, or the canvas. Once I issue the plotting command, it plots onto the entire canvas. All right. And you would notice that I didn't specify any X or Y here. By default, when you're plotting, and these are just basic plots. So if I'm plotting and then I specify just a particular set or a list of entries, what it does is it picks those entries as our Y, and then it will use their indexing or their positions as the X. So if you notice, Python starts its indexing from 0. So this element 10 is on position 0. Element 2 is on position 1. 39 position 2, 4.2 position 3, and 5 position 4. So by position, this is 0, 1, 2, 3, 4. All right, even though we have 5 elements. So if you notice, first it picks the 0 position, plots that against the 10, goes to the 1, plots against the 2, goes to the 2, plots against the 39, the 3 against 4.2, and then the 4 against the 5. And that's by default, I mean, just simply how the plotting works. And with this, we are just using sample data. Now, if I want to plot, say, two particular arguments, so say an X against a Y, then I would have to define my X. So let's say I have here also another 5, a list of 5 elements, say 1, 3, 4, 8, 9, and then I plot these two against each other. Now, this identifies the first part as our X and then the second one as our Y, and then the plot. Okay, so this is just basically how the plotting feature works in Python. I'm taking time to go through this because we'll need it subsequently. Now, also what we can do is we would want to add, say you want to, you are just using the simple linear plot. So if you want to indicate the markers, you would probably want to specify the markers. There are more simple ways of doing that. By default, if I just pass in a string here and I pass in, say, a color, say R, it automatically knows that this is a red color. I pass in, say, O, it knows that there's a marker. The marker is, I mean, just, we have circles in this case, all right? And then there are no lines. So it just picks red circles, and then the markers are circles, we have the reds. If I want the lines in there, I just bring my line, and then it connects them. This is one way to do that. Now, in order not to also be confused, you can try the second alternative, which is to specify your color as, say, red or R. It still works. You specify your marker as, say, circles. Okay, let's change this so that we know if it works. Let's change this to blue and then maintain the same circles. Okay, all right. And then you notice between every element, there is a comma separating one from the other. Now you can put everything on one line, but just for us to understand, I'm doing them on separate lines. And then you can pass in your line style. If you don't want a line, just set this to none. Sorry, I think the none should be a string. Yeah. Set this to none, and then it doesn't show. But then if you want, you know, dash lines, you can just put in 2 dashes or type in dashed, and then that also works. If you want dash and a dot, I think that should work too. Yeah, that also works in here. So you can specify whatever you want, indicate your marker sizes. For instance, I want to increase the marker sizes. Just pass in marker size, say maybe 20. Okay. And then, yeah, there are a whole lot of things you can do. And then you notice this is all for just the plot line. So all the attributes in there for everything that's plotted within. Now, if you want to add your text on the end, you can just add in. So we have plt.say y label to set the label on the y-axis. Say, let's say this is just values. Okay, and then it places the text values here. Of course, you can increase the font size from here by just bringing a comma font size and specifying your font size, say 14. Let's increase. So similarly, you can do same for the x-axis. So let's say we have plt.x label and then call this say index or whatever. and that also works. You can of course also set your titles, and then you are good. All right, so this is just to give us a fair idea of how this works. Now, if you're also interested in having your legend, of course, you would first need to define a label in the plot. So we have to specify here, say a label, and call this dummy plot. Now, when you do this, you've only created the label, but you've not created the legend. So the label is sort of creating a label for this plot we have. Now, in order to show the legend, we'd have to type in here plt.legend, and then the legend shows. All right, and that's what we have over there, telling us, I think the markers are too big. Let me just reduce this a bit to say 10. And that's just a fair idea of how this works. All right, so now with that same mindset, we understand what this is doing here. So first, we are just plotting. We create our figure canvas or the interface. We set the figure size. This is the length by the width. So 12 inches by 5 inches. And then we now plot just 20 random numbers. And this is what we get. Okay. And then we do the same thing. We do the same thing this time, setting the x as a range of 20. That's from 1 to that's from 0 to 19. So np.arange 20 would create, if you have np.arange, it will just create a default of 0 all the way to 19. That's one less than this, and these are 20 elements. So we pick those 20 as our x, pick the 20 random numbers as our y, and then just plot them. Okay, so these are just quite simple to understand. So with this mindset, we can then move on. Now, if you want to do same for, say, panel plots, multiple plots, what we can do in this case is first create your figure, create the axis. Now, what this means is that we are creating the whole figure environment, and then we'll create the axis, which will be representation of the individual panels. All right. There are very easier ways to go around this, where you create your figure first and then add the subplots. I don't know. Let me just try and then add that one to it. So let's say first we have a fig. Equate that to plt.figure. This is the default approach, what you would see most often. And then from here, we'll create our axis. So let's say AX, and then we pick the figure, and then we add subplots. Okay, and then by adding the subplots, you have to define. So by adding the subplots, you have to define first how many rows, how many columns you need. So let's say I need 2 rows by 2 columns, so 2, 2. In fact, you can just put it together, but then if it goes beyond 10 individual elements, it means you will suffer. So that's where you bring in the comma. So 2 rows, 2 columns, and then you specify which particular one it should be placed on. So let's see the first one. Now, in this case, for the plotting, the indexing doesn't start from 0. Okay, you need to understand the structure. So with this kind of plotting, the indexing doesn't start from 0. So once we have this, it means we have 4 by 4 created, and then the first panel or the first axis is what has been picked. So if we plot anything, it goes into this axis. Now, if we go to the next end, and then we now add another axis, I'm going to override this. Okay, it's not going to change this plot because that would already be plotted before the second one. And this time I specify that 2 by 2 position 3. Now I expect this to come under it. If I specify the position 4, it goes to the right hand side. So you have 1, 2, 3, 4. And this is the very basic way you see that the subplots are created. It also comes in handy when you have different projections, which we'll talk about probably in the session 3. Okay, so rather than doing this, now you notice that if I'm generating this, I'll be doing this over and over. So if I need to plot something out, produce the axis first, create a plot in it. When I'm done, go to the next axis, create a plot. And this takes a lot of time, especially if the axes have similar properties. So the simpler way to do that is to just define your figure and then what we call the axis. Let me use that as a plural. And then we call our plt.subplot. And we specify the number of columns, number of rows directly. It's not in any particular order. So n rows can be say 3, n calls can be say 2. So let's say we have a 3 by 2, and this is enough to create the 3 rows by 2 columns. Now, if you also want to specify the figure size, then just like we did, you can pass in your fixed size and then indicate your figure size in terms of the width, the length and then the width. So let's use a 12 by 8. So we have something like this. Okay. Now, we need to understand this from a matrix perspective. This one is different from the first one. In the first one, you had at every point you were specifying the number of rows, number of columns, and then the particular position to be, for the plot to be placed on. Now, in this second aspect, what you have done is you've already defined the entire figure and the axis. So you have the figure interface, and then we have the axis already created, 1, 2, 3, 4, 5, 6. Now, these are treated as matrices. So in a normal matrix form, when you have your I and J position, sort of position locators, this will be 0, 0. The next one, 0, 1. When you come down here, this will be 1, 0, 1, 1. And then you come down, this will be 2, 0, 2, 1. Okay. So think of it this way. All these are 0 on the X, 1 on the X, 2 on the X, and then the vertical 0 on the Y, 1 on the Y in that order. So you have 0, 0, 0, 1, 1, 0, 1, 1, 2, 0, 2, 1. So if you want to place a plot in any of them, it's easy to pick the particular axis. So for instance, I want to fix this in the fourth one, which is the second the one in the middle on the right, so center right, which is position 1, 1, because it's 0, 0, 0, 1, 1, 0, 1, 1. Yes. So 1, 1, I pick the axis, specify the row and the column. So axis 1, 1 dot plot. And let me just plot random numbers. So say 20 random numbers. Now, because I called the axis, it goes there directly. All right. So with this, you can, handle any of the axes quite easily because, of course, they have similar properties. If I also want to set any of the axes to, a transparent form, it's quite easy. I can just pick, for instance, let's say I need this axis not to show the first axis. So that's axis 0, 0. And then I just set the visibility. So set underscore visible, and then I set this to false so that it's not visible. And okay, I think I typed something wrong. Oh yeah, sorry, there's an I in there, visible. So set visible, and then we set it to false, and then automatically that goes off. So with this, it's easy to pick any of the axes and then just manipulate the axis alone. And that's the beauty of this. All right, so if you went through the task last week, you see that it was used in there, and then this is the explanation. So this typically does same thing. So the same plot we generated in the first, now we create 2 rows, 2 columns, and just pick the particular axis we want. Sorry. So we just pick the particular axis we want and then produce this visualization in there. And that's typically like what I've explained already. All right, so this is just the preamble. Setting the background for what we will be doing. So now if you go back to the task we had, we started with the X array, looked at how to manipulate it. And so we're given 4 tags. The first one was to split the crew data into 4 climate regimes. The crew data was from 1900 to 2020. And this was just a dummy data. So I already have my data here. So I'm importing the X array. Of course, I've already imported this. I may not need this again. And then I'm importing filter warnings to ignore the warnings, which I explained last week, that this helps, to maintain some sort of sanity on your page. There are some warnings which are not errors. Without this, the warnings will still pop up. And if I don't want to see them, I'll just ignore them with this package. All right. And so now with my xarray imported, we have xr.open dataset because we imported xarray as xr. So xr.open underscore dataset, we pass in the name of the data. And then with this, it will just open the data set, and the data contains a variable called PRE, and I explained from the day one. So I mean, if you are new, you would have to look at it to see this explanation. So with this, we select just the precipitation data and assign it to the variable DA, and so we can check what the DA contains from here. All right. So it loads our data, and then it tells us, okay, there's a data, it has 3 dimensions, 1,440 time steps, 146 latitudes, 150 longitudes, and these are their respective positions or their coordinates. And then this is just the precipitation data recorded in millimeter per month. This is the monthly data. All right. Now, if you look at the dates, it starts from 1901 to 2020. So we are splitting them into 4 climatic regimes, which is 30-30-year intervals. So we have climatic regime 1 being 1901 to 1930, the second one being 1931 to 1960, third 1961 to 1990, and then 1991 to 2020. And so when you pick the data set, the data array, which is our DA, which we have over here, with the cell method, which is to select, we can specify our time, which is the dimension of time, and then we slice. So we are slicing over a particular time. So our time window, bear in mind the time is a date time, but currently if you look at it, it's treated in here as a string. So I'll need to specify this also as a string. So I specify, for instance, my climate regime 1, 1901, comma, 1930. And this will just slice. So if you look at this, this is the entire data set. Now, if I run this slices only the 1901 to 1930. And that's just what we wanted. All right, so we are splitting this into climate regimes 1. So this becomes say DACR1, which is climate regime 1 data set, or the data array. Okay, so with the same mindset, that's what we just did over here. So the first part of the task was just to slice the data over these time windows. So 1901 to 1930, 1931, 1960, 1961, 1990, 1991, 2020, and then we give them different variable names so that it's easy to compare and to do some assessments with them. All right. So the first part of the task is handled easily by just slicing through the data set. All right, now the second part says we should visualize the long-term climatology. That's the climatological means and then their respective standard deviations. So for instance, before I come to what the solution is, if I pick, in this case, we've run this, if I pick DA underscore CR1, which is a climate regime 1, it has the data for just that period alone. So with the data for that period, I can simply find the mean, for instance, over the dimension of time. That means these are 3 dimensions. If I find the mean over the time, it means I'm finding the unit mean across the time. So the time dimension sort of collapses, and then we are left with just a 2D output. Okay, so this will be the mean across the time for these 2 dimensions. So once I have this, it's easy to just plot and see what the climatology is just by adding the dot plots, and then we can see clearly what the means are, or the monthly climatologies are over the entire region. Okay, so this is what we are just going to do here. So first, okay, that's one step if I'm just doing the monthly aspect. Also, the very first session, we looked at the grouping. So it's also possible with DA underscore CR1 to group the data set. So we apply the group by method. So we had your climate regime dot group by, and then we pick the time component, and we said the time is a date time, so you can group it across, say, a year, across the season, across the month, across any particular window. These are defined. So if you need more details, you look on the XRA URL I gave in the lecture 1. And once we do this grouping, so when we do this, this will create year classes. So we have all the 1901s in one class, 1902s in one class, up to 1930. Now, if you want to find the class mean, so we find the, for instance, the sum. I want the yearly total, so the sum across the individual time windows. Now, what this will produce is it changes the time now into years. That's what the group by does. So we have 30 years. The time dimension, the name time has changed to year, because this now is understood as yearly data. And I said this is one of the difference between group by and then the resample. So once we have this, if I want the climatology of all these, now I can find the mean this time, not over time, but this time over year, because once we do the grouping, it changes this from time to year. So if I'm finding the mean after doing the yearly totals or the yearly characterizations, then it means now I'd have to find the mean across the year. And this will give us the yearly climatology. That's the mean annual total. And so now if we plot this, we also get the mean annual total. And you notice that this is slightly different from when we just did the monthly climatology. Okay. So with CR1, with the monthly climatology, you see the extent of the values as high as 250 because this is per the month, but then this is per the year. All right. So we then find the accumulations over the year, and then we now find the climatology with the mean. Okay. All right. Okay. So this is what we'll be doing here. You can apply any of them. You can apply the first one or apply the second. Now in the solution here, I applied the second one. That's why I had to explain this also. So of course, we've already imported Matplotlib, so I don't need this again. So just as we did at first, we create the figure, we create the axis using the plt.subplot, specify the number of columns and the number of rows. Now, this is a 4-column, 2-row plot. So we have 4 columns, 2 rows, and then our figure size of 18 inches in terms of the length and 8 inches in terms of the width. All right, then I'll come back to explain this. All right, so let me comment this one out so we see what works. All right, so what we are doing in here is after creating this axis, let me just copy this so that it's easy to explain. All right, so now I create the axis alone here and then I plot. If I do this, the axes they've already been created, but this plot is not assigned to any axis. So you notice that the plot just goes wherever it fits because I mean this was the final step I was running. That's why it's there. Okay, but I needed, for instance, this plot to be in the first one. Then it means what I have to do is there's a keyword in the plot called AX, which assigns the axis. And then I have to specify which axis I want it to go into. So for instance, I need this in the 0 by 0. So what I'm doing is all the climatologies should be in the top part. So the first one, which is the CR1, should be in 0, 0. Second one, that's the CR2, should be in 0, 1. Okay, so with this, you can specify the axis, and then it goes directly there. And that's what we have here. And if we want a uniform color bar for all of them, then in that case, we wouldn't need to show the color bar here. So we'll just add the keyword add color bar, and we set that to false. So that means this will be plotted without a color bar, right? Okay. And then because we want them to also be uniform, we'll have to set the minimum and maximum values. So I can set the minimum to 0 and set the Vmax, which is the maximum. So see, these are yearly groupings. So let's see, we set this to 2,500. Okay. And then you can also set the color map. If you think this color map is not what you want, it's easy to set the color map by passing in the C map, and then you have a whole host of color maps you can use. All right. So now this is how this is working in this place. All right. So that's exactly what we are doing here. Now we plot the CR1 in the first panel, which is axis 0, 0. Plot the CR2, the same thing, but in 0, 1, which is the second on the top row. And then the CR3 on the third, the CR4 on the fourth. Now, because we want to create a uniform color bar, all of them, we use the same Vmax. The Vmin by default, we're going to be 0, but we can still specify that in here. And so what we'll do is we could assign all of these at any point to CB or to any keyword. So what we are doing currently is the final plot should be assigned to a variable, say CB, so that we can use that CB to generate the color bar. Okay. So what we've done in here is now we've created all these plots. So let me copy all these ones up again so that we just have the output for those ones. Okay. So now let me cut out this final line. So we have these plots. It's taking a while, but it should be done soon. Okay. All right. So we have all these plots for the 4. This is the first one for the CR1, CR2, CR3, CR4. Now, in the final part, we've assigned this to the variable CB. Now, with the figure, which is the fig over here, we can then create the axis. So what we are doing is we add an axis to the figure, all right? And then we specify the position for the label to be placed at. So we want the color bar to be placed on this right-hand side, okay? And so placing this on the right-hand side, think of it this way. This is like an A4 sheet or like a paper. It starts from 0 to 1. The top to bottom also starts from 0 to 1 in the top. So every position is a fraction of, the distance of 0 to 1. So if I need this on the far right, then of course my x first, which is the 0.9. So I'm telling this to be placed at position 0.9 on the x. And then in terms of the y, 0.55. So x would be somewhere towards this end. 0.55 will be somewhere slightly above the midpoint in terms of the y. And then once we do that, now we specify the width. So this is the x interval. That means from 0.9, stretch this by about 0.01 inches, all right? And then from 0.55, stretch this by about 0.35 inches. That means this should be how long or how tall it grows. Okay, so once we specify these ones, it means we can assign this to a keyword. It can be anything. Let's use, for instance, CAX here. And then now we specify the color bar by adding the color bar to the figure again. So we have fig.color bar, and then the color bar should be created with this final plot, what we assign to CB. So it should be assigned to this, and then it will be placed at the position that we defined, which is the CAX over here. Okay, so once we have that, let me take these ones out first. Once we have this and we run, it should give us the output we want. But then, of course, you can specify the orientation. That's okay. You want this to be vertically oriented, which already it's vertical. But then you can still, include it. If you want it in the horizontal, you can always include that. And then we want to extend the range. For instance, the values here seems to be darker blue than what we are having. So it means there are some values above this threshold. So we would have to extend, and you can extend both ends, which is the highest and then the lowest, by specifying both, or you extend, say, the maximum alone or extend the minimum alone. That also depends on you. All right. Now you notice that because our plot extends all the way to the end, even though we place this at 0.9, it is still lying on the plot. So that's where this subplot adjusting comes in. So we have the plt.subplot adjust, and then we specify that the far right of the plot should be 0.87. That means we'll have a margin of about 0.13 left. That's white space of about 0.13 left. Okay, so this would be 0.87 will be the farthest our plot can go. And then there'll be a white space there, which, of course, once the white space is created, then we can place that label in there. And then we also specify the width spaces. That's the space between each one. That's from left to right. You can also specify the height space, which is from top to bottom. So we have width space of 0.5 inches, height space of 0.5 inches. Now, if we replot this gives us something better. And that's what we have over here. And this looks more presentable, right? And so that's the explanation to everything that's been done in here. So if with the same mindset, that's exactly what we did over here in the top. And then in the lower part is the same thing we've done. We group them by time, find the sum, which is still, of course, the yearly totals. And then in terms of the climatology, we rather find the standard deviation instead of the mean. So the only thing that changes here is the mean. The mean changes to the STD, which is the standard deviation. And then the axis, instead of being 0, we'll start with the 1 because we are going to the bottom part, all right? And then we set the minimum and maximum extent. Now, this is standard deviation. Of course, there could be negative and positive, so we just use a divergence color, which is red, blue. And then we, of course, create the same axis additions and then add the color bar. And then once we run this, we would have all two sets of plots showing both the climatological mean, and then the annual climatological standard deviation. And that's clearly what we have here, right? And that's, as simple as it gets. I think I need to subplot adjust again on this so it becomes better. All right, and that's how this works. Okay. Please, while I'm going on, if you have any question, you can still ask so that I know we are following or I know what else to touch on. Okay. And so once you have your visualization, you have your output, the next is just your interpretation, which of course comes to what you are doing. All right. And the third task was to create a latitude by month Hofmolar plot for each climatic regime. So of course, I've already explained this top part, so I'm just moving on to the next. Now we pick, for instance, the climate regime 1. We group them by the month as a time.month. There's already a monthly data, but grouping by time.month means instead of having respective month per years, it's going to put all of them into just 12 classes. So if you look up here, without the group by, this is how the data looks. It is already a monthly data, but they are months of the year. So you have January 1901, February 1901 in the order. But then when we add the dot group by and we group it by time to month, it only creates 12 classes. So all Januaries together, all Februaries like that till December. Now, if we find the mean over the time, it means we are only going to have 12 data points, which is an entire climatology. So if you look at this, we have 12 points of months for every grade. All right. And then you notice that we are creating a latitude by month Hofmolar. That means we want to conserve or preserve the month. So if I find the mean over the time, it still is going to be left with the month. And then of course, if I find also the mean over the longitude, then the longitude is collapsed. Ideally, the time was collapsed into 12 months from the original 1440, and then the longitude also then is collapsed, and we are left with just the latitude against the month. So if I add to this the longitude, it means it creates just a final output of data array which contains only 12 months by a total number of latitudes. And of course, once we plot this, there's a 2D. So once we plot this, it gives us, a contour plot. And this is typically the Hofmolar. If I need the latitude on my y-axis, then it means you just have to specify y to be latitude. And then you can specify the x as month. Oh yeah, sure. It is lat. So we had lat, not latitude. So I did a wrong thing. So lat. And that's it. And then we have the latitude against the month. All right. So this is what we just did in here. So we found the mean over the time and then the longitude, and then we plotted. All right. Of course, by plotting with this, we have more like an IMSHO plot. So if we want the contour, we can just specify here that, okay, just give us a contour plot. If we want the contours to be filled, then it means a dot contour F would work, and we define what type of plot we want. Okay, so that's all what we've done in here. All right, and then of course we are assigning CR1 to the first axis. So there's also a 2x2. So if you look here, we would have a 2x2 plot or 2x2 panel, and so the first one should contain that. So once it's 2x2, 0, 0 is the first, 0, 1 is the second, 1, 0 is the third, 1, 1 is the fourth, and we add those. Make sure there's no color bar showing for all of them. Assign it to the final one to say a variable, and then use that variable to create the axis, and then we'll have as simple as this. All right. So all these I've already explained, so that's why I'm not going into detail again, because it's the same procedure that we are repeating, right? And of course, you can just pick any of the axes and then add a title. So we just set a title for it, and then we have the CR1, CR2, CR3, CR4 in that order. And then the final task says using CR1 as a reference. So we pick the first climate regime as the reference. We estimate the magnitude of change. That means when you pick the first one, we pick the climatology of that. get the climatology of the respective climate periods and subtract it from the reference, so that we know whether it is an increase or a decrease, which is positive being wetter, negative being drier. Um, I don't know which nuns you're talking of. No. Okay, I get it from the data set. No, currently, so none means typically nothing in there. So X-array by default, when I find the mean, it doesn't include the none. But if you also want to be, again, if you want to go the next step, then what you can do is you can rather apply. So in fact, you can use the reduce method. So for instance, I pick DA underscore CR1, okay, and then one of the things we need to be clear on is that these are nuns because they are oceanic data. So those points, I wouldn't have any data at all. But if this were on a continent, where, for instance, if I'm finding the mean, then it means the none could have an influence. Then it means in that case, what I'll do is I'll just use the reduce method, okay? And then I would make use of my NP. So NP has a non-mean, which is to find the means without the none. So for instance, let me first use the NP. So we have A to be 1, 2, 3, 4, 5, and we find the mean. Let me use NP.mean of A. This gives us the mean of A to be 3. Now let's pass in here, say an NP.none. So that means A contains a missing data somewhere. Sorry. Sorry, so NP.none. Okay, so A contains a missing data somewhere. Now if you find the mean of A, sorry, NP.mean, NP.mean, this produces none because it doesn't know what this value is. So if you want to sort of omit this, then we would have to make use of the non-mean so that the nuns are ignored, but then we still find the mean of the data set. And this time the division would be just by the total number of non-missing data. So it will be all these added together divided by 4. And that's the value we get. All right. So if I want to do the same thing in here, then it means I'll have the dot reduce being applied, and then I'll specify the np.none as the method. All right. And then I'll specify the dimension to be applied on. So just as we did the mean over the time, I'll specify the dimension over here as time, and then it will produce the same output. Okay. So you notice that there isn't any difference in the first one, this one. There isn't any clear difference because, sorry, let it show. Yeah, so there isn't any clear difference. If you look here, there's 18.044731 is the same thing. Because like I was saying, the nuns we are having are data over the oceanic point. So if it's none, it means there was none all throughout. And this is, of course, monthly data. So the continents have data. That's why when we even pick any of the points, for instance, I select the time, say 2020-01, okay. Okay, yeah, CR1 is up to 1930, so we don't have this. So 1930-01, and then I plot this. This gives you a fair idea. So you see the data is only over the continents. There are no oceanic data. All right. Now, we would come back to handling this. That's the final part of how to clear the oceanic data, of course, because you notice that I think there was one which I did, and then the ocean was all changed to zeros. Right? There's a way to clear all those ones, which I'll look at towards the end. All right. So I believe your question is sort of answered. Okay. So the very last part is we are trying to estimate the change. So if I pick the climatic regime 1, for instance, I perform the annual totals. All these are annual totals for the respective climatic regimes. Okay, so these are annual totals for the respective climatic regimes. So we have the variable DA claim underscore CR1 being the annual total for climatic regime 1 on and on till the fourth one. Now, if I pick, for instance, DA claim, okay, let me run this first. So DA claim this. Now we have the years against the latitude and longitude. So of course, if I find the mean over the year, it means, of course, we come back to the same annual sort of the mean annual total we talked about, the climatologies. So if I have this, you notice that there's no time component now. It's just the latitude against the longitude. There's just a climatological information, which of course I think we've already visualized this. So if I have this, and then I have same for, let's say I have this for, say, CR2, and then I subtract the CR1 from it, this should give me the difference. All right, so I can put all these in a bigger parenthesis, to get the difference, and then I can plot, and this will tell us where it was getting wetter, where it was getting drier. Okay, so with this, you already know. We've not changed our color scheme, so by default, this is telling us the red is wetter, the blue is, drier. And if you want to change that, of course, you can just specify your CMAP, and then this should be red, blue. So that's red lower, blue higher, and then the blue becomes the wetter, the red becomes where it's getting drier. Okay, so that's exactly what we've done in here. So with the same basis, we pick the first one, we plot just the CR1, we plot that, we do not add the color bar, we give a maximum value for it, and then we have our text. So this is just going to plot the CR1 data the way it is without any difference, nothing like that. And then when it's done, it will generate a single color bar for just that one alone. Okay, and since that's on the very first point, we have 4 columns, no rows, so we just use the position 0 for that, and then we place the color bar under just that one. And so with the same analysis or the understanding I gave based on this part, that's what we use to get the color bar. And then we come to where we do the difference. So we find the climatological differences, and we plot them on their respective panels. And we set the V min and then the V max, so -50, maximum 50. And then we set the color map for all of them. We ignore the color bar. And so on the final one, we give it a variable, okay? And then we place the text, the titles on all the various axes. And when we are done for all of them, all the remaining ones, we now generate a unit color bar for them. Okay, so we specify the axis, how long it should be. They should be horizontally placed, and it should be extended on both because we have extreme negative, extreme positive values. It should have a label of difference in millimeter per month, and then it should be plotted based on, the color bar should be based on the CB we have here. This is the variable in the final part, and then use the axis that we specified up here. And so with that same mindset, we are now able to generate first our climatic regime 1 rainfall data. That's the mean annual total data, and then the difference of each climatic regime from that. So with this, you can clearly infer from this that, okay, this climatic regime is getting wetter than maybe the very early, the early part of the 20th century. And then you also, compare the other climatic regimes, and then you are able to make some inferences into that. And so this was the task from the last week, and that is like the beginning part of today's session. So with all these, it's easy to do any visualization of a sort in Python. Now, I don't know if there are any questions. You can throw them in now before I look at the final part. All right, okay, so I'll still go on whilst maybe you get your questions through. Now, the next thing is using the where method. So with the where method, you can actually apply this on the data set or the data array, which of course I've explained what the difference between the data set and data array is. So we have our DA being our data array in this sense, okay? Now, think of it this way. the latitudes stretch all through. So if I pick, for instance, the first time, for instance, and then plot that, see that this stretches all the way over the entire Africa. Now, what if I want data only across the equatorial region? Then I can make use of the where method to subset the data, or sort of mask. Think of it as more masking than subsetting. So we can use this to mask just all the other parts out. So all we are going to say is that we pick this DA and then dot where, and then we have to specify that within this DA, wherever the longitude of the, let me use the latitude, wherever the latitude of the DA is, let's say, greater than -5. So the equatorial ranges are the -5 to 5. So where the latitude is greater or equal to -5 as one condition. All right. And then also where the latitude is lesser or equal to 5. That's the far northern part. Now with this will just pull out the data for the tropics, and then all other parts that already had data will be changed to none. So by default, it will change all of them to the remaining parts to none. So if I pick this, and for instance, I pick just the first time and I plot just the first time, you notice that the first time will have just the data across the equatorial regions alone, and all the other places have been masked. Now, if I want to replace the masking with, say, a particular value, say all those should be changed to 9999. That means wherever we've not selected should be changed to the value I'm setting. So you notice that all those values have a different criteria. Okay, so it's easy to use this as a form of masking to mask your data. If I don't specify the alternate value, then they are all set to none. Okay, and that's typically what we have in here. Okay, now if I don't want these masked areas to show, then it means I can specify that let's drop this. So drop should be true. That means it should really drop them. And then you would notice this. So by default, the drop is false. Look at this thing again. Look at the latitude stretch. So all the latitudes are showing, okay, from the -30 something to +30 something. Now, if I set the drop to true, it only shows the equatorial regions. All right, all other areas are cut out. And so I can just use this to subset the data and then save this as a new NetCDF just by, instead of plotting, I can just pick this and say, okay, to NetCDF, and then give it a new name. That's okay, save this as, say, equatorial region .nc. And then this will be written as a new NC file. Okay. All right. So that's how the where method works. It helps you to mask your data. It helps you to also do some selection of a sort. So there's the first part where, of course, we have already shown how this works to select the equatorial region, for instance. You can also use the where method to pick some specifics. Let's say if my data were daily data, then I can use this to select, for instance, rainy days, which of course is something widely used. Rainy days, R10 events, R20 events, the percentile events that are beyond a certain threshold and all that. Okay, so let's think of this as a threshold. For instance, in this case, we are trying to select monthly rainfalls that are greater than or equal to 100 millimeters per month. So what we are saying is that pick this DA, and then wherever the DA values are greater or equal to 100, just select those ones alone. Okay, but don't drop the others. Just leave the others the way they are. And then when you are done, this is just the where method where it's been applied. Okay, and then when we are done, we should just create year groupings. So after selecting all the values that are greater or equal to 100, we create year classes for them, and then we are just getting the count of these events. So this time we are not adding the events together, we're only counting them. So if every year we had about, say, 20 of those, the next year we had 30, let us know the count. So that's all we just doing here, and then we would have the annual event counts. Okay, now this is stretching all the way from 1901 because it's the entire data array, so 1901 to 2020. But then, of course, we can select a particular period. So let's slice just 2011 to 2020, and then we plot them. Okay, now let me take this one out first. So by slicing the years, we have only data for, say, the 10 years, which is 2011 to 2020. Now we can generate a facet plot. If you just want to have a quick look into your data, just a facet plot, you just have your dot plot, and then you specify your call wrap. That means, okay, the column should be wrapped after every, say, 5 columns. So this can be any integer value. So all I'm saying is that, okay, plot first, second, third, fourth, fifth, and then wrap it, come to the next one. Okay, so think of it as just a normal, when you're using a Word document and you select a word wrap. Now, if the word fills the line and then it doesn't go onto it, it already moves it to the next line. That's exactly what we are doing. And we are telling this to be wrapped based on the year. So we are plotting the columns based on the year. And then once we have 5 in a particular row, we'll go to the next row. And that's all we've done here. Okay. And this creates a facet grid for us, or a facet plot. And so with this, you can easily, visualize your plot. So if even for all the 120 years, we could have done same, that would take a longer time. So now if I specify here to say 8, it means it's going to create 8 columns. And then after meeting the 8, the remaining parts will be taken to the next in that order. Exactly. All right. So you can have the whole lot together and they all have a uniform color bar. All right. And I've already explained that we can use this for data masking. So, I wouldn't go into this one again. Now, let me explain something from here. So for instance, we have, when we pick the RD count, you notice that all the regions in the ocean are still shaded purple. You might do some accumulations and then the nons will be showing like a least value, but then your bigger side has a lot of value. So you want to use the where method to select the ones that are not necessarily sort of nons or are not false data. So for instance, in this case, we have a annual RD count, which is this. And then we can specify that, okay, so wherever, so the dot where method, wherever the annual RD count is greater than 0, it should pick those ones. All right. So it's going to pick only the ones that are greater than 0. And for instance, I just want the first part alone, the first element alone, and then I plot that. Okay. And so instead of showing everything, you see that every part that showed 0 is already taken off. All right. Now, the only trouble or the challenge you have in here is if your continental data also shows some zeros in this case, but this is like a fair deal. It works well. And of course, if you have the data sets, you have 2 different data sets with the same sort of resolution, and then their resolutions are the same, you can sort of accumulate one, and then when you accumulate that one and you see that, okay, only the ocean data doesn't show, then you can use that particular one as the criteria here. Okay, and then when you use that one as a criteria, then it will be able to manipulate this one to suit. All right, there are some examples I've used them in. Time wouldn't allow me to show them, but of course you can use the where method to do all these sort of data masking, and it makes your work easier. And all we are doing is that pick this condition, wherever this condition is true, select those ones, ignore the other ones. If you want to drop all the other ones, then you add just the drop true. Okay, and so that's what we've done in here. We pick wherever the monthly mean. So in this case, the RD count, we also generate a mean of the RD count wherever is greater than 0. Okay, we pick just those ones. Now we select a particular set of years and then we just plot them in the facet grid approach. And that's what we have. Okay. All right. So of course you can also use the dot sum. I think that should also work. Yeah. That's it. All right. So so that's been that for today. Today the focus is just on the visualization and the XRA where method. Now if there are questions, I would probably take some. You might want to unmute yourself and then ask, and then we'll take a few questions.
Hello, sir.
Yes, please go on.
Please, thanks very much. About this thing, your meeting days, like some of us know, we are not that aware of it.
Uh,
So, can you please tell me the days that you usually do this?
okay. So officially, I mean, the links were sent out for people to participants to register. So it means you probably didn't even get the earlier communication. So this is just running for 4 Mondays. This is the second Monday. So the first, let me just stop sharing this so I can share the flyer instead. So if you look at this, the very first one was on 27th February. I believe you can see this, right?
Yes, please.
So the first one was on 27th February. That was last week. And this is the second session. We have two more sessions. That's day 3, which is the 13th. That's next week, Monday, and then the fortnight from today. Yeah. And it's always 17:30 to 18:30 UTC.
Okay. Thanks very much.
All right, sure. So please, if there are any questions, you can ask. And then so today we intentionally didn't put any task at the end so that you can actually spend some time to go through the very first and the second. And then hopefully in the remaining parts, that's the day 3, day 4, day 3 will want to focus more on the projections if you are using some geographical maps inclusive. Now you notice that in this case, we're just plotting. You could see the feature because the data was covering the entire continent. So that's it. But if you had your maps, how do you also inculcate your map so that it becomes visible? And yeah, those are some of the things we'll tackle in the third one. And then hopefully in the final session, we'll be doing some verification plots. So you have a whole NetCDF data, and then you have, sometimes you want to generate some Taylor diagrams and then some error diagrams and all that. So we use the verif tool. It's very easy. It's also a command line interpreter, but we've also sort of imported that into Python and then have a dummy script, sort of a sample script that makes the whole procedure easier. So yeah, if there are no questions for me, I would end my session here. But then, yeah, those are the activities for the next week and then the next 2 weeks. Yeah. So please, if there are any questions, you can ask. Yes, please. Yeah, Chris, please go on. Mm-hmm. I didn't
I
get
want to
your
know
question.
the
Can you
function
can
of
you take it again?
the, the function of the fig, the FIG before comma before the distance,
Okay, before the
the
axis.
PLC dot subplot. No.
Okay. All right. Yeah. So like I explained earlier, think of it this way. Think of this as a sheet of paper. Okay. You can't just start and create the panels. The panels are just the axes. So the axes are just the smaller, spaces we've created in there. So each axis has a particular sort of identifier. But then the entire interface or the entire sheet you are producing all these smaller panels on are the fig. So for instance, if you look at this where even though we squeeze the whole figure interface to fit up to say 0.87, because we still had that whole white sheet as our fig, it was easy for us to add the legend on that fig, okay, which was like still drawing on that white sheet, but then not necessarily attached to any sort of small sub panel or like small panel on its own. You get it? So that's the basic mindset. Think of it like you're having a sheet of paper which represents your figure. Okay, the fig itself is that sheet of paper. And then the axes are okay, you've drawn like smaller rectangles on the sheet of paper. And in each smaller rectangle, you have a particular image. You get it? So once you're creating the PLT dot subplot, you would of course have to define the figure you are working on before the axis. Without this, you confuse your system. I don't know if it's clear. And then I explained that from the top when we started. I said the default way that this will be done. I think this wasn't even added to the GitHub page, but I spent some time to go through this. I said the default way is that we create the plt.figure and we assign it to the fig. And what we are doing is now we add the subplot as a particular axis. Okay, and instead of doing this multiple times, like I've explained here, I said the easiest way is just to use the fig and the axis all together and define just a plt.subplot, specify a number of rows and columns. Okay, and then there'll be instances where this might not also be so useful. For instance, in this case, I told you when you have something like this, the properties are quite similar. So if these were all projection-based plots, like map projections, then it means all of them with map projection plots. But if I wanted to have like a map projection and then as well as say a plot that's not map related, then of course I would go in for this one instead, because with this I'm able to add on and define a particular subplot to be say either map projection or not. Okay, so that's it. I mean, those are some of the things to note. It comes by making use of the tool over and over and over again. Yeah. I believe your question is answered. So if there are any other questions, we've already exceeded our time. So if there are any other questions, we take them quickly and then before we end the session.
Hello, sir.
Yes, please go ahead.
Please, the selection of the over the tropics before dropping the none over the distance. I mean the ocean side, no.
Mm-hmm.
Because after dropping of it, the image has turned somehow, let me say, vertical.
Is that it changed to what?
Is it this? It turned to a vertical column instead of horizontal.
No. It was still the way it is. So yeah, it was still the way it is. I think maybe you are looking at it differently. This, right? We selected the latitude. We are saying that the latitude 5 and then -5 should be the threshold. You get it? So it's the same plot without the where method. Look at it this way. Without the where method, this is how the plot looks. Okay. And then now think of it this way. Let's say let me intentionally give this a fig and axis here so that I would explain it better. plt.subplot, and then let's say this just a normal 1 thing, so equals to 1. Okay, and then AX should be axis. Okay, now there's the plot. Now think of it this way: axis dot sorry. Okay, so now look at this. Look at the area we've cut out. Okay, I've intentionally drawn this line there so that this is showing the region we cut out. We said the equatorial region is just -5 to 5 degrees, so 5 degrees south, 5 degrees north. So this is the region where we are cutting out. So now we have this, and we are saying that, okay, so sorry, let me undo this so that I just take it to the way it was at first, and it's easier. Okay. All right, so I have this. I mean, this was just a lazy man's way of doing this, so for the want of time, I didn't want to go back and type everything. Okay. First, let me check if we have the D1 already even in it. Okay, yeah, there's D1. All right. So AX equals to axis. All right. Okay, so look at it this way. So it's the same area we've cropped out, okay? And we've maxed out all the other areas, all right? Now, if I set my drop to true, it's the same region we've cut out, okay? It's not changed horizontally or vertically in any way. It's the same region. Now, I intentionally placed these blue lines, the blue lines there, so that I see that it's the same region we've cut out. Is it clear?
Yes, yes.
Okay,
Thanks.
sure.
Mm.
All right. Okay, so we would like to end here for time's sake, and I would encourage you to still go through the materials. They are still on the GitHub page. Um, we always send them to you via your mails. Again, I'm still sharing it here via the chat so that you can, if you're not aware, you can still connect. And this again is also currently live on the MeteoData page on YouTube, and the recorded session will still be uploaded again. So, I mean, you can always check back if you have any issue and then get back to us. Let us know how we can be of help to you. All right. So, thanks for the time, and then wish you all the best and see you next week.